Welcome back. We're in week 4 discussion of bonding. Okay, in the previous week, week 3, okay, week 3, let's capture what we have done so we have a broad idea on what we're going to get into. In week 3, we learned nomenclature. That is, given a compound, we identify whether it's ionic, covalent, or transition metal based on, okay, if it's ionic, it's typically an alkali or alkaline earth metal and a non-metal. Okay, that's what makes it ionic. Okay, and if it is covalent, okay, it is two non-metals, a non-metal and a non-metal. Okay, and then we learn how to name transition metal compounds. Okay, they are not technically ionic, but you can sometimes consider them ionic. But and then we had a transition metal and a non-metal. Okay, we only classified them based very rudimentarily on the type of element it is. Okay, second, we learned about the electronegativity difference. Okay, electronegativity difference based on the Linus Pauling electronegativity table, okay, to classify the bonds, okay, as ionic, polar covalent, and non-polar covalent, aka covalent, right? Now this is about the bond, not about the molecule. Okay, non-polar covalent, aka covalent. Okay, and then we learn how to draw structures, basic structures. Draw structures. This is what we learned in week 3. Okay, now for week 4. Okay, week 4, we are going to learn classify the molecule, okay, classify the molecule as polar or non-polar, okay, based on its electron pair geometry. Okay, and we would also learn about molecular geometry. Okay, that's the agenda for this week. So we're going to classify the molecule as polar or non-polar based on its electron pair geometry, and we're also going to learn about molecular geometry. Okay, so that's the agenda for this week. Okay, all right, let's go get a couple of molecules to help really understand what we're talking here. Okay, because this concept is very long, okay, this particular concept will be split in 2 or 3 videos. Okay, and as I said, classify the molecules based on its electron pair geometry, right? And that's where the VSEPR model comes in. Okay, as I've already said, don't worry too much about how long this title of this concept is. Valence shell electron pair repulsion theory. Okay. Okay. This concept has its own deficiencies, which we'll talk about later. Okay, but that's what the expansion of the acronym VSEPR stands for. It's valence shell electron pair repulsion theory. All right, let's go get two molecules, BH3 or BCl3. Let's take BCl3 and PCl3. Okay, right? Let's go get our valence Roman numerals for boron, which is 3A, and chlorine is 7A, right? Similarly, phosphorus is 5A and chlorine is 7A. Okay, not much has changed since end of week 2 discussion. Okay, it's still the same. Okay, so as I said, the element that is least in count goes at the center, and the element that is more in count goes on the outside. Okay, so boron goes in the center, and it's got 3A, so that means it's got 3 valence electron. Chlorine's got 7, so it's got 7 valence electron, right? So the 3 electrons, just put them anywhere you like, doesn't have to be in a particular order. Okay, just put them around boron. Okay, now let's go get a different color for chlorine. So Cl has got 7, right? And as I said, if you have 3, 4, 5, 6, 7, anything past 2 electrons, you've got to split them into pairs of electrons, right? So if you split 7 electrons into pairs of 2, you would have chlorine something like this, right? Pairs of 2 and an odd electron, right? That's what we have, right? So that means we connect. Let's go around and actually draw the 3 chlorines that we have. Each chlorine has 7 electrons, so we split them into pairs of 2, and then so we would be left with odd electron. Keep in mind, it's the odd electron that's going to bond, okay, with the odd electron from the boron, right? So let's bond them. It's what we learned, okay? And then if you do the electronic configuration difference, okay, boron I believe is 2.1, boron's 2.0 and chlorine's 3.0, right? So that's boron's 2.0 and chlorine's 3.0, right? So the electronegativity difference is 1, right? 3 minus 2 is 1, right? So let's go get a different color, right? So boron is less electronegative of the two, so the chlorine gets the head of the arrow, boron gets the tail, same for the reminders, right? Don't worry, I messed up my because of my artistic skills, all these arrows look of different size, but that has nothing to do with it, okay? All right, so now if you write this as a shorthand notation, right? Now what is this electron pair repulsion, right? Right? That has to do with not the electron pair on the outside atom, it has to do with the electron pair on the central atom. This right here, folks, is the central atom, okay? That means if the central atom has a electron pair or lone pair, then that contributes to the molecule's polarity. At least that's what VSEPR suggests, okay? Now if you notice, boron has nothing left. It only had 3 electrons and it shared all its 3 electrons with the 3 chlorines, even though the bonds themselves are polar covalent. Remember I said the molecule itself is nonpolar. How did I make that connection? Is because I'm going to call from now onwards my central atom as A, okay? Okay, I have only one central atom, so it's A, and my outer atoms has X. So I have 3 X's, 3 chlorine, so 3X. Okay, if it is AX3, okay, and then that means it is Trigonal Planar. Okay, that's the name of the geometry. You would have to remember this. I will give you a summarized list at the end of all this. Trigonal Planar. Okay, that means it's like, if I redraw this molecule, let me actually get rid of the PCl3 out of the picture so I can draw it on the next screen. I just need this to be, I just wanted to point that out. I can get rid of it now and actually draw it on a fresh screen. Okay. All right. AX3 is trigonal planar, right? So it's like boron is at the center, okay, and the 3 chlorines are at 3 corners of the boron. So if you connect them, you don't, I mean, this is, I'm just showing you, because trigonal means it's a triangular and it's planar means it's on the plane of the paper. Okay, so trigonal planar means it's like a slice of a pizza. When you cut a slice of a pizza, does it have a 3-dimensional shape? No, it sits on the table or your plate, right? That means it's planar, right? That's big. The reason it's triangle or trigonal planar or triangular planar is because the central atom does not have a lone pair, right, or a pair of electrons, right? So it's trigonal planar, right? What that really means in terms of the polar bonds, you can ask me, you mentioned the bonds themselves are polar covalent, then why is the molecule non-polar? Okay, I'm going to prove that to you. Okay, this is how the plane looks like, right? And we said that the chlorine is more electronegative of the two, boron gets the tail, and same thing for this, same thing for this, right? If you think about it, these 2 arrows are going, you know, in the downward direction, right? Just looking at it visually, just think of it visually. So overall, this arrow is going down, this arrow is going up. We now have a tug of war, right? The 2 tails are clashing, are pulling each other apart, so they're canceling out, okay, canceling out. So the molecule itself is non-polar, okay, because there is no electron pair repulsion in this molecule, because there is no lone pair in this particular molecule, which is why it's called non-polar. Okay, very good. Now all we are dealing now with is electron pair geometry. Molecular geometry would be a complete video on its own, right? Now let's go get, this is a difficult concept to get your head around, so if you don't understand it right away, watch the video a couple of times, you would sure get it. Okay, let's write PCl3 now. Okay, now we said phosphorus is 5A and chlorine is 7A. Okay, that means this has 5 valence electrons and this has 7 valence electron. Okay, now as I said, the element that's least in count goes in the center and the element that's more in proportion goes on the outside. So we're just going to put them anywhere around the phosphorus. Okay, now phosphorus has got 5 valence electrons, so I'm just going to go put the 5 somewhere in the ballpark of the phosphorus, and chlorine's got 7, so we are now going to go split the 7 electrons into pairs of 2. So now, as I said, these lone pairs have no effect on the molecule. It is what's on the central atom that makes the difference. Okay, so again I do that for all my chlorine. So I can split the 7 electrons into pairs of 3 and then odd electron is left out. Okay, write them as a pair together. Okay, don't stretch them too far. All right, now let's go get our red color back. Okay, and connect the blue and the black dots. Now, it doesn't matter where you connect it, they are all the same. So I've connected it. Now if you quickly notice, I got 2 odd electrons left on the phosphorus. Okay, so when I'm going to come back is I'm going to actually erase it out of here, okay, and put it right next to the 1. Okay. Now that's a lone pair. That's where the valence electron pair repulsion theory comes into picture. Now let's highlight it with probably a green. Let's get a dark green. Okay. Okay, that's a lone pair right there, right? So now if you go get the electronegative difference, and which I'm not going to do, is you would notice that phosphorus is less electronegative than chlorine. Well, I might as well go get this so that I can show you too. Phosphorus is 2.1, okay, and chlorine is 3.0. Clearly this is more electronegative of the two. So if we go get our blue color back, we can say that the tail faces phosphorus, head faces chlorine. Same for this. Don't worry if your arrows are not all of the same length. That has no implication whatsoever in understanding the concept. Now if you notice, okay, just like how we wrote it from now onwards, as I said earlier, the central atom is A, the three outer atoms are X, so X3. But then this time we have a lone pair. Lone pairs we're going to call them by the letter E. Okay. Okay, so we have AX3E. We are basically encrypting the molecule into letters, okay, which is easier to manage. So it's a central atom, three outer atoms, and a lone pair, right? Now if you draw this molecule, just visually looking at it, okay, because of this lone pair, you know, it's called trigonal pyramidal, okay. It's not planar. What people think is because it has three atoms to the outside, it's going to make a triangle. It would have made a triangle if it was not for the lone pair. Okay, so technically what happens is the lone pair pushes all three arrows downwards. Okay, this is not an information that you don't know, so I'm going to draw it this way. Instead of it facing to the side, the lone pair is acting like an umbrella and it's pushing all the arrows down. That means they're all acting in only one direction, which leads to a cumulative arrow going down. Okay, you've got to remember this somehow. I don't know how you would, but you have to remember that just because a central atom is surrounded by three atoms, it's not triangular planar. What this is it looks like the pyramid of Giza. So it looks like this. Okay, so if this is the phosphorus, this is the chlorine. Okay, all the arrows are pointing down. Okay, why? Because of this lone pair that sits at the top, which was absent in the previous example. So AX3 is trigonal planar, AX3E is trigonal pyramidal. Because the arrow is pointing only one direction, there is nothing to counteract it on the opposite direction. This molecule is polar. So typically when you have lone pairs, the molecule is polar. Typically when you don't have any lone pair of electrons, typically the molecule tends to be non-polar. Okay, that's a trend. There are exceptions to it which we might see, but as a general rule, typically when your molecule has this E, it leads to polar, and if the molecule is missing the E, you will see that it is non-polar. All right, so I'm going to stop here for the first two molecules, and then in the next video I'm going to talk about three more geometries. Now we are learning electron geometry, okay, which is different than molecular geometry, which will be a video in its own. All right, so stay tuned for more videos on electron geometry involving the valence shell electron pair repulsion theory, or VSEPR. Stay tuned.